Hi, welcome back to this recording. Look, sorry, I cut the other bit short because I wanted to stop at a particular point and I just thought it was better just to stop. So I just edited the last bit of it out. So let's just have a quick recap what we looked at. We designed a model for an LED so that then we could put it into our equivalent circuit. And ultimately, we want to work out what the value of this resistance should be. So we've decided that this LED here, the LT4223, can be represented by a 1.7 volt constant voltage source and a 13 ohm resistor, and that's close enough for what we need to know. As long as we're aware, again, that we can only use it over this range of the curve. So next we're going to have a look at this part of the model. Now this requires us to dive deeply into a few things in the microcontroller. We don't have to analyze the circuits in the microcontroller. We can figure out what this is going to be. But first of all, I want to talk about VCC. This is the source of voltage for the microcontroller. And there are some things about VCC that you need to know, okay? The first thing about it is that there's a range of voltage. We actually have a maximum operating voltage of, well, let's just have a look at the data sheet. So we've got the data sheet here. We have got, let's see, operating voltage. Voltage on any pin except reset, minus 5 volts to VCC plus 0.5. VCC is the thing of interest here. So VCC, maximum operating voltage, is actually 6 volts. Now, I've tried operating these microcontrollers myself at 6 volts and I wouldn't recommend it. I found it hard to program. They actually worked okay, but they didn't want to program. So actually, I tend to run them around 5.5. So the maximum operating voltage is 6 volts. Now, let's just have a think back at the next stage here, and that is depending upon the speed at which the microcontroller is operating, we've got a different range of VCC. So for low speeds, we can go down to 1.8 volts. So from 0 to 4 megahertz, we can run the microcontroller from anywhere from 1.8 to 5.5 volts. From 0 to 10 megahertz, we have to run it from 2.7 to 5.5. And from 0 to 20 megahertz, we have to run it from 4.5 to 5.5. So you've just got to think about this and see how it overlaps here to start with. If you're working at a low speed, you can go to a low voltage. And if you are working at higher speeds, so you cannot go to the lower voltages, you have to be at a higher voltage, okay? And this, why does this sort of interrelationship exist? Well, it's got to do, it's to do with the heating effects perhaps of what's happening inside it, but certainly the transition delays and how quickly a microcontroller can transition between 0 and 5 volts, or 0 and its VCC, which we're not going to go into any detail, okay? But just suffice to know that if you're going to run a microcontroller at 16 megahertz, which is, you know, what we're doing with our 18 mega boards, the Nano board, the Arduino Uno board, they're running at 16 megahertz. So we can't run them down at these lower voltages. They have to be run at the higher voltages. So here's just a couple of simple questions. Could we design a circuit that ran at 4 volts and 16 megahertz? Well, no, we could not, okay? We've got to run it at 4.5. Now, maybe it would work, but you don't want to go outside those specifications for any sort of commercial product. Could you run it at 7 volts and 12 megahertz? Well, absolutely not, because 7 volts is beyond the specification. Absolute max was 6 volts for these devices, okay? And typically 5.5 is the maximum you want to go to. Now, could we run it at 1.8 volts and 4 megahertz? Well, yes, we can. We can run it at 1.8 volts and 4 megahertz, okay? So these are just some simple specifications. Now, could or should we design circuits that use an overclocked AVR because our specification goes to 20 megahertz? Well, the answer is absolutely not for any sort of commercial application, okay? Definitely not. You might get away with it, and I have tried and got away with sort of 22, sometimes 24 megahertz and playing around with them, but actually you don't want to do that. No, not for a commercial application. Stick to your specifications. That way, if something goes wrong, you can always point the finger at the manufacturer, okay, and not yourself. Now, right, so this is part of the VCC. We're still looking to try and figure out what this resistance is. And so we dive into the data sheet a little bit further. And here's some really interesting specifications. Now, these specifications, actually, they're not from section 32.1 of our current data sheet. I think you'll find that these, and I'll just fix this, yes, they're in section 29.1. So that referred to a slightly different version of the data sheet. So what we're looking at here is we're looking at the maximum current that can be passed through a pin of a microcontroller, an I/O pin, and that is 40 milliamps. But conversely, there's another interacting factor here that you need to think about, and that is the DC current on a VCC or ground pin cannot exceed 200 milliamps. So you can't run all your I/O pins at 40 milliamps because all that current has to go through either the VCC or the ground pin as well. So these are a little interrelationship. So this is where this 40 milliamps comes from. So just because you can run one pin at 40 milliamps doesn't mean to say that you can run all of them at 40 milliamps, okay? And that was not section 32, but 29. Okay, so what we're going to have a look at now is we'll have a look at this particular graph, okay? Now, again, we're looking at a voltage current relationship, okay? So this one here, you'll notice that the voltage is the Y and the current is the X, which means that as we are changing the current, this is what's happening to the voltage. But I want you to think really clearly about what voltage we're looking at here, okay? This is the voltage on the pin when VCC equals 5 volts. So we've got a 5 volt source here, and what we're measuring is this voltage here when there is a current of some milliamps through this resistor. So obviously you can see that if there's no current through the resistor, we're at 0, then there's 5 volts on both sides of the resistor, okay? But as we draw current, the voltage drop across this resistor will increase, and therefore the voltage on the output will fall, okay? So let's have a little think about this. If we're at 85 degrees Celsius, then what's going to happen is we're going to start at 5 volts, and as we draw more current, it's going to follow this subtle curve here. And you can see that it is a subtle curve. We're going to treat it more or less as a straight line, actually, for our purposes for analysis at the moment. We won't go into any complexity. Again, this is because this is an average curve, a typical curve for a microcontroller, just like the typical curve for our LED. There's going to be some subtle variations, but it is close enough for us to be able to work with it and figure out what's going on. So we're going to work at 85 degrees C. So that means that we're using a microcontroller inside an environment which is heating up for some reason. So you can imagine it might be inside a heat pump where it could go from minus 10 degrees even, or something like that, up to 40 or 50 degrees perhaps inside the actual heat pump unit itself. So let's just take a look at the 85 degrees. So what that means is that as we're drawing more current through this resistor, the voltage across it is increasing and the output voltage is reducing, okay? Just that standard voltage divider action again. So if we've got 20 milliamps through the resistor here, that means that we've got 4.4 volts at this point here, which means that there's a 0.6 drop across this resistor. We've got a VCC of 5 volts, but only 4.4 volts is available to our load if we're drawing 20 milliamps. So that works out at actually a resistance of 30 ohms. And because this graph is straight enough for our purposes, we'll stick with this as being a straight line, 30 ohms, okay, at 85 degrees. Let's take a more common temperature, 25 degrees. So at 25 degrees, what we've got is at 20 milliamps, we have something which is a bit less than 4.5 volts. And if this is 4.4 and this is 4.5 volts, then I've said that this is 4.48 volts. So I've arbitrarily said something around about that point. There's no point in getting particularly picky about this because, as I say, these are average nominal curves and we'll just work with that close enough value. So what we've got here is at 25 degrees Celsius, we've got an output voltage of 4.48 volts, which means that this straight line represents a resistance of 26 ohms. So at 25 degrees, our output resistance is 26 ohms, but at 85 degrees, it goes up to 30 ohms, okay? So there's a couple of sort of ideas. So now we're beginning to understand what's going to influence this resistor value. It's going to be influenced by our output circuit. It's going to be influenced by this VCC voltage, and of course this resistor value, which changes with temperature. Okay, so let's have a look at our particular board. So this is the explained Mini, the same as the Arduino Uno, the same as the Arduino Nano, and our VCC on that is 5 volts, okay, typical sort of 5 volts. And the crystal frequency, of course, is 16 megahertz. So now we're going to have a look at actually putting this circuit together. What have we got here? Okay, so what we've got here is we've got 5 volts. I'm making that assumption that it's 5 volts. And I've also got to make an assumption that it is 25 degrees, okay? We know that this voltage here is 4.48 volts at 25 degrees. And if we look at this circuit, what we've got is, we can work it out with your voltage divider, you can work it out through Ohm's law basics. All right, as what I've done here, I'm going to look at it from a KVL perspective. And that is starting along here at this node here, which is 0 volts or ground. I'm going to just go around my loop until I get back again to it and find out that, hey, the voltage across here is VCC, right? So that's the first term. The next term is the 20 milliamps, which is flowing in these 3 resistors here, okay? So what we've got is 20 milliamps, we've got this resistor, the source resistor, our current limit resistor in the middle, and the resistance of our LED, okay? And then, of course, what I've got is I'm subtracting also this LED voltage here, and that will all sum up to 0. And the reason I'm going plus, minus, minus is just the same sort of standard KVL that you would normally do. This direction of this voltage is this way, and the direction of this voltage is in this way, opposite to the current, okay? So we've got voltage arrow this direction, we've got voltage arrow this direction, and we've got voltage arrow this direction. So it's this one positive, these two negative, and we end up with this understanding here, okay? That's our KVL. Now, just reorganizing that, we end up with this particular rearrangement. We end up with R limit, okay, which is what we're trying to work out, of 126 ohms. Now, there's no such thing as a 126 ohm resistor in normal practice. You could probably buy them, but actually what you standardly buy is E24 series or E12 series, where you've got 120 ohms. Now, if I make this 120 ohms, that means that the current's going to be slightly more than 20 milliamps. And actually that's not too bad, because our LED is fine with that, our microcontroller is fine with that, so we can get away with 120 ohm resistor. And the interesting thing is, of course, if the voltage increases, if the temperature increases, this resistance here is going to increase from 26 to say 30 ohms or a little bit more, and the current's going to come down just a little bit. So what we'll find is if we want about 20 milliamps in our LED to get it to its correct brightness for us, then we'll put a 120 ohm resistor in here. And that's how I've worked it out. Now typical practice is just to say, I'll put in a 100 ohm resistor if you want it to be bright, and put in a 1K resistor if you want it to be reasonably dimish, okay? But in actual fact, what we're working out is if we want this particular LED to have 20 milliamps flowing through it to make it a particular brightness, then we're going to need about 120 ohm resistor here. And that's a great starting place, okay? So now I want to just think about this. Remember, I said that we've got 20 milliamps in this IO pin here. Now, what we need to know is that how many of these can we connect to the microcontroller? Because all of the current from the LEDs has to come back through the ground pin. And so that means that no more than 200 milliamps can be allowed to flow through this pin of the microcontroller. And again, that's sort of just standard heating practice. If the pins are only a certain size metal, then you don't want too much current, because that causes heating effects. And of course, if these circuits are soldered, then that means that the solder could ultimately degrade over time. Not melt so much, but actually degrade from heat over time. So how many LEDs? Well, what we're going to look at there is the fact that the maximum rating is 200 milliamps. But that's 200 milliamps for the whole device. Now, we're talking about more than the LEDs that we're connecting to the device, part of the circuits that are inside the microcontroller are already drawing current. And these are going through the ground pin as well. So therefore, we cannot have, for instance, 5 LEDs each drawing 40 milliamps because there's already other current demands made upon the microcontroller. So have a quick look at the data sheet, and we might have to look somewhere to see what would be the current for our idle of the microcontroller. So when it's just sitting there doing normal calculations without anything. So what I'm going to look at here is to say that power supply current here at an idle of 8 megahertz and 5 volts, well, it's drawing up to 5.5 milliamps. So that means that we no longer have 200 milliamps to play with. We have about 195 milliamps we can play with in terms of current limit. Okay, just remember that. So, and depending on which features of the microcontroller you're using, timers, ADC converters, analog comparator, some of those sort of things actually draw more current as well. Okay, so what we're saying is that about 5 milliamps is being drawn just by the microcontroller itself. So we can't use all of that 200 milliamp capability for our LEDs, okay? So that sort of wraps up these introductory specifications of the microcontroller. I want you to just grasp these ideas about the fact that the microcontroller VCC works, the voltage depends upon what frequency you're running it at. Low frequencies, if you want to have a low voltage, you've got to work at lower frequencies. Right? So if you want a higher voltage, then you've got to, if you want a higher frequency, you have to work at a higher voltage. And our device can have, yes, 40 milliamps through an I/O pin, but you can't do that through too many pins because the current will all sum and come out of the ground pin, and you don't want that to exceed 200 milliamps, of which about 5 is already being used by the microcontroller itself. So, to be on the safe side, you could run 4 high current LEDs from this device. Now, what if you want more? Well, in the next sequence, we're going to look at how to add other devices, the field effect transistor, which will give you this capability, okay? Cheers.